Hello everyone, welcome to another class, physics class. Today we'll be taking the second part of the reflection of light. And I want you to pay rapt attention, take notes, and make sure that you are very attentive. I'm going to move straight to the board right now, and please, once again, pay rapt attention. Here we go. Reflection of light, part 2. As I go on with this, I would try to just touch a bit on some of the things we looked at in the first. I'm not looking at them in details, but I just want to touch a bit. So I'm going to start, when we talk about reflection of light, let me talk about images again. I mean, the kinds of images that we have, we said this in the first class. We have the real image, and we have the virtual image. And we define the real image as, real images are images that can be caught on screen, on a screen. So for these images, light rays. For these images, light rays, give me a second. Give me a second, let me put my other device on silent mode. Okay. So real images are images that can be caught on screen. Light rays actually pass through real images. So light rays pass through them. Keep all these points in mind. Let's go to virtual image. Or let's say virtual images are images that cannot be caught on a screen. And the idea here, it is, there are images through which rays do not actually pass. Okay. Or let's write it this way: light rays do not actually pass through them. But they are still visible to the eye. So keep that in mind. And we made a point about lateral inversion in the last class, but I don't think I defined it verbatim. I mean, I don't think I gave a clear definition of it. So lateral inversion, this is the effect on plane mirrors This is the effect on plane mirrors of objects placed in front, whereby the appearance of the image looks like a reversal of the object. So just keep that in mind. Let's keep moving. I remember the picture of lateral inversion is something like this. Let's say this is what you have. Let's say I have FIS here. What I'm going to see is kind of SI, so something like this. So this is the picture. So let me see if I can rewrite this as more like something like this. Instead of this, it goes like this. Yeah. So this is the idea from this to this. So that's lateral inversion. Let's now talk about an important subtopic: images formed by inclined mirror. That's a very important one, and this one shows up in exams. When two mirrors are placed at an angle to each other, let me make that statement. When two mirrors are placed at an angle to each other, the number of images formed, the number of images formed is given by n equal to 360 over theta minus 1. So please keep this in mind. Let's just take 1 minute. Observe this formula. Let me put it in red. It's very important. Look at what it is called. When two mirrors are placed at an angle to each other, that angle is angle theta. The number of images formed is given by this formula. Take 1 minute to make sure that you have that formula well written in your notes. Please and please take 1 minute to do that. Very good. I believe you have done that now. That formula is super important. So let me also write n is the number of images. Number of images. Theta is the angle of inclination. So keep in mind, let me put it as notes. You know the way we normally put notes. When theta equal to 180, the two mirrors will act as a single mirror. And therefore, please keep this point in mind, form only one image. So when it's 180, and we can clearly see that by the formula. If you put in theta as 180, you have 360 divided by 180. That will give you 2 minus 1, 1 image. So whenever you have theta as 180, two mirrors out as a single mirror. Then another case, when theta is 0, the two mirrors are parallel to each other. And the image is formed at infinity. Get that point by even simple algebra. In this place, if you put in 0, normally anything divided by 0 gives us infinity. So the idea that we see from there is very clear. Put in theta as 0, the image will be formed at infinity. So just keep that one in mind. Let's now look at another subheading. It says effect. Let me change my ink. Effect of mirror rotation on reflected ray mirror galvanometer. Don't worry. Let's get that subtopic down. Effect of mirror rotation on reflected. Sorry, this is reflected, not on a reflected ray mirror galvanometer. Effect of mirror rotation on reflected ray mirror galvanometer. Now let me talk about this. If the direction of an incident ray on a mirror is kept constant and the mirror is rotated through twice that angle, if you keep the incident ray constant and you rotate the mirror through twice that angle, this concept the direction of an incident ray on a mirror is kept constant and the mirror is rotated through twice that angle, the concept is utilized in what we call mirror galvanometer. Used to measure very small electric current. So it is used, this particular concept, keeping incident ray constant and rotating through twice the angle, is used for mirror galvanometer and in navigator's sextant. So mirror rotation is useful in mirror galvanometers and navigator sextant. So please keep that in mind. Keep that in mind. Let's see if we can walk through an example. Okay, let me. Okay. Yeah, let's pick this example. The reflection, let me see this. The reflection of a narrow beam of light incident normally on a plane mirror falls on a meter row parallel to the mirror and at a distance of 1 meter. Calculate the angle of rotation of the mirror if the reflected beam is displaced (21.26 centimeter) along the meter room when the mirror is rotated. Take note of how we are going to solve this problem. The solution is, excuse me for a bit. I'm going to use the formula tan 2 theta just keep this in mind, tan 2 theta equal to okay. Currently I'm supposed to have a diagram to typify this question, but I'm missing the diagram. So what I will just do is try to get the diagram out, or better still, we'll move forward and revisit this in the future. But let me yeah, just keep this in mind. I'm going to somehow try to figure out the diagram for this later, or just leave it out for now. We're going to solve that some other time, or something similar to that. But for now, the question isn't complete without a diagram. And we need a diagram to be able to determine if we'll be using, what rule of trigonometry we'll be using to determine our, solution. So let's not just make assumptions. Let's move forward and then, revisit something like that later on. Let me quickly highlight. I would love to talk about the uses of a plane mirror. Uses of a plane mirror. And that includes, number one, it can be used as a periscope. Keep that in mind. Number two, it is used in kaleidoscope. When I say as a, I mean in a, not as, in a periscope. It is used in a kaleidoscope too. Then it is used in sextant. Keep that in mind. Keep that in mind. Yes. So take about 1 minute to catch your breath. I want to make some points. Just give me a minute. Quickly do that. I want to highlight some important things like the angle, let me call it angle of deviation. I want to define that. Then let me just call it points to note. Angle of glance. So angle of deviation is always equal to let me give you the formula. (180 minus 2i). Keep that in mind. So where I equal to R, or will I say, let me put like I equal to angle of incidence. And that is also equal to R, which is equal to angle of reflection. We are dealing with reflection of light. So keep that in mind. That's for angle of deviation. Then talking about the angle of glance. The angle of glance is equal to 90 degree minus I. So, and in a similar vein, I is also angle of incidence. So please keep that in mind. So please take note of these important concepts as you study and prepare. Yes, yes, yes. Let me go straight into reflection on curved mirror types. I'm also going to talk about the images produced, the uses of these mirrors, of curved mirrors, uses of curved mirrors, and mirror formula. So that's what we are going into now, capitally. So when we are talking about curved mirror types, we need to talk about curved mirrors first of all. So I'm going to introduce the concept of curved mirror. Let me say types of curved mirrors. The first one I'm going to call is concave. Concave or converging mirror. Please take note of this naming. It's not exactly the same thing when it comes to lens, when it comes to lenses. So please pay attention to what I'm saying now. Don't just trivialize everything. Please don't come to class and play with it. Take note of what I'm saying right now. When it comes to naming mirrors, it's not the same thing. it's not just pari passu, or ceteris paribus. I mean, all things being equal, since I know that concave mirror is also converging mirror, it means concave lenses are also converging lenses. That's wrong. So please, this is specifically for mirror. Why I'm saying this is that concave mirrors are converging mirrors, but concave lenses are diverging lenses. So please just settle that one in your mind, first of all, now that the naming does not go, it's not like vice versa, it's not vice versa, it's not as this one, so is the other one. No, mirrors are different from lenses. Thank you very much. So types of curved mirror: concave or converging mirrors. 2, convex or diverging mirrors. So we start with concave or converging mirrors. What are these kinds of mirrors and how are they formed? Let me put it this way. Now, before I could have told you how curved mirrors are formed first. Let me put that in a note. Let me move this downwards and just tell you how curved mirrors are formed. Right here, note. Curved or spherical mirrors are formed when a shell of hollow, I think I mentioned this in one of my classes. Yeah, where I talked about using, maybe I've talked about it, or maybe not, but let me mention curved mirrors. Let me just talk about it afresh. When a shell of hollow sphere of glass is made out of a piece of glass and then silvered. So please keep that in mind. So specifically now, concave mirrors. These are formed when glass is silvered from outside so that light can be reflected from inside. Very simple definition. Nobody intends to confuse you or stress you. Keep this definition in your reservoir of knowledge. And please be serious with studying, especially for your exams. So now, this is an important point that has already been made. Let me draw how it looks for you. Looks something like this. So this is the part that has been silvered. Because we say silvered outside. Silvered or hard surface is what I'll call this place. So now we can now point to this other side and say light comes inside from here. Generally in mirrors, there's something called the principal axis. I'm going to draw that through the center. This is the principal axis, this particular thing, this particular line, rather. On that line, we have this point between the mirror, the point where this principal axis meets the mirror, and then there is another point right here, which we call the focus. Distance between these 2 points is called focal length. Then, if you extend that focus by 2, that is, here we have 2F, and that particular point is called center of curvature. So keep that in mind. 2F, center of curvature. So this surface through which light comes inside this place is called the reflective surface. Pay attention to that. So I believe you get that diagram. Let me move it downwards a bit. So please pay attention. We have talked about a couple of things right now. And then this is the diagram of a concave mirror. That's how it looks. Let me quickly talk about a convex mirror. Convex or what? Convex or diverging. That's in the case of mirrors. Please, this is not exactly how it is in lens. In the case of lens, the convex lens is converging lens. So I'm trying to quickly emphasize it so that there is no day you are going to assume that, they are the same in mirror and lenses. No, they are not. Thank you very much. So convex or diverging mirror. Now, how are they formed? These are mirrors. These are formed when coating is done so that reflection this time around is from outside. You know, in the case of concave mirror, we had reflection from inside. So reflection is from outside. So the idea here is I'm going to draw it like this. So this one was like this, but this is now going to be like this. So we have the principal axis running through. And this point here, just like the way you have it here. Let me put it in red. This point here. This is like, yeah, this point P. I believe that that P is generally called the pole. Later on, but just keep it in mind that there's a point P, at least for the mirror. So you have then you have the focus. Let me extend this line. Then you have, like, over here, you have 2F. You know what? That is center of curvature. Center of curvature. And most of the time, that focus or center of curvature, which is also 2F, we can write it as C. So just keep that in mind. So light travels, you know, through here, then reflects, because this is the reflecting surface. Let me point at it. This surface now is the reflecting surface. So that's how a convex mirror works. So when light travels Oh, let me use my red again. When light travels through this line, it reflects, bounces like this. And then also downwards, I'm going to put one down, travels here, it bounces. You see that? And it bounces like that. Then the leftover of that bounce, let me draw it better. Leftover of that bounce so leftover of the bounce, is what gives you what gives you your your image. So we'll explain, but just get this as the fundamental diagrams of how the convex mirror works for now. And then you will start seeing clearer pictures as we go on explaining concave and convex mirror. Quickly, let me talk about some important parts of curved mirrors, the essential part, those things I was mentioning, like curvature and all of those things. So let's see, essential parts of curved mirrors. I'm going to mention them and explain them immediately. The aperture. The aperture, this is the width. Let me explain that well. This is the width AB of the mirror. So keep that in mind. And you see that's a very short definition. The pole, that was the P I was talking about. Let me see, was there any point I put AB in? Okay, let me remove this AB. So let me move this. So when we're talking about width, of course you can tell. See this? That's how thick the mirror is. You get it? So same applies to the other one. So that's the width of the mirror. And the pole is this is the center of the reflecting surface of the curved mirror. Keep that in mind. There's another one called the center of curvature. This is the center of the sphere of which the mirror forms a part. So the idea is that the center of curvature is more like, if you complete, I don't intend to mess up my diagram, but if you complete this guy somehow, let me do that again. Okay. So let me use the convex mirror. If I say I'm completing this now, I'm going to go out of the stuff, right? But let's say I'm going to complete it somehow. If I'm going to form a full circle, let me put it that way, that center of curvature will fall at the center of that circle. That's the idea. So it's a very straightforward idea. So let's go on. Then let's talk about the radius of curvature. Keep this point in mind. Radius of curvature is the distance from the pole to the center of curvature. So the idea is, this radius of curvature is one of the things that determines what type of mirror we're using. The radius of curvature for a concave mirror the radius of curvature is in front. Obviously, if we go back to our diagram, see it. The radius of curvature, like we said, is what? The distance from the pole to the center of curvature. That is, we're talking about this distance from here to here. Let me draw a straighter line from here to here, because this is the pole here. From the center of curvature to the, to the pole, that's the radius of curvature. You see that for a concave mirror, it's in the front. In the front area. It's in the front. This is, the front. But for a convex mirror, this is the front portion, but you see where the radius of curvature is. Let me do that again. This is the front, right? And this is the back. You see where the radius of curvature lies for a convex. It lies at the back. So the idea is, for concave mirrors, the radius of curvature is in front. Why for convex mirrors, the radius of curvature is behind. Straightforward point, or can be a very key exam question. Please, your study habit should not vary with your, your mood of how they, are we calculating a lot? Are we also, just, doing theory in class? It should be based on how well you want to do your exam. So take both theoretical classes and calculational classes as serious as, as each other. Like, no one should be more serious than the other. But this point I'm making now can make you, if you take them lightly, you can fail almost 10 multiple choice question rather. So please pay attention. Don't say we are just saying stories. No, these are important points. Go home or go to your hostels or go to your wherever you are. Read them, reread them, master them. That is the work that you are doing now. So number 5, another point is the principal axis. Principal axis. The point I'm making here is that this is the parallel line. This is the parallel line. That was like the first thing that we drew through the curves. The parallel line that runs through the pole and center of curvature. Like we all were able to see the principal axis in my diagrams. This middle line, that main line that runs through the pole and runs through the focus and the center of curvature. It runs through PFC. So keep that in mind. The principal focus. That's our F now. The principal focus. Let's talk about that. Principal focus. This is, but this time around, we're going to talk about it for a concave mirror and for a convex mirror. So we're saying the principal focus for a concave. Let's start with for a concave mirror first. For a concave mirror, principal focus is the point where rays that are parallel and close to the principal axis appear, or let's put it like that, appear to converge after reflection. So you see this definition of principal focus. Let me put it like this. Let me show you what is happening. Let me take my green line to this place and see these rays that are traveling now. When they hit this place, they reflect back and converge at the focus. The one traveling down here goes like this, hits this place, and reflect back at the focus. So it is coming like this, and bounce back like that. So you see what's happening? Let me do that again. Let me remove it. This was the diagram before. Focus now on the green line. Let me zoom in. Focus on the green line. It's moving. I said if light rays are coming like this now, and they hit this mirror, they bounce back and they form at the focus. If they are coming from down here and hit this place, they bounce back and form at the focus. So that's why you see diagram going like this, this one now bounce back. So look at the explanation. Let me go to the explanation. And you see that as they are coming back, what do they appear to be doing? You see something like this. Let me just draw what's happening here. Something like this, bouncing back. Yeah. It appears as if they are meeting at a point, right? And that point is what? The focus. You see that idea? So that's the idea you see in our definition that says the principal focus for a concave mirror is the point where rays that are parallel and close to the principal axis appear to converge after reflection. Oh, please keep this. And I did not just teach you, I did not just give you theory, I showed you in the diagram. So they appear to converge after reflection. So keep this in mind. You know that from the idea I just showed to you, we can easily derive the definition for the principal focus for a convex. We can easily get for a convex mirror. We can easily talk about that. let's go back to the diagram for that one. If I zoom in, I already showed you what was happening here with the red. But I'm going to put the green on it now and do it again. See it? It's moving like this. It hit this place, then it bounces back. Then we are saying this other one too, coming like this, hit this place, then it bounces back. Then when it bounces back, if you now look at the other side of its movement, if you look at the other side of its movement, that point, if you consider that point, do you know that normally the rays that we produced, this part that we produced, you know, this part is the imaginary part. This part is imaginary, right? This is what was actually produced. So we are seeing that if we really consider the actual that is bouncing this way, and we also look at this one that is coming this way, if you look at it very well and you trace them, you know, backwards, like this and like this, you will discover that this focus here, it's appearing as if from this point, they are spreading out. The idea is you have a point like this, and those other 2 points are spreading out from it. What is that idea called? When you spread out, you are diverging. You diverge. When you gather, in this particular one, they were bouncing like this, and they were gathering together at a point. When they gather, they converge. But this other one, this is the point in consideration, this particular point here, pointing at it again. They appear to be, you know, diverging from it, moving away. So that idea is called, you know, divergence. So you see, just in a similar way that we defined the principal focus of the convex mirror, we are also going to define for this one and say it is the point where rays that are parallel and close to the principal axis appear to what? To diverge. Are you getting it? To diverge after what? Reflection. Do you see the idea? Yes. Very important. So that is a very good point. And then we can now go to an important formula. Or before we do that, let's make a very serious point. Very serious. We can now say, based on what we have explained, the focus, that F point, the focus of a concave mirror is real because converging rays are seen. One of the ways you can use to the logic you can use behind this is just that if you discover in the case of this guy, I want to put a mark to just mark it. In the case of this guy over here, that is the concave mirror, the whole idea we talked about here. Let me erase that again. But you know what I'm talking about. In the case of this diagram, you discover that it is the actual things that were the one that was coming like this, that bounce back, the one that was coming like this, that bounce back, that formed the focus. So it was not, we didn't trace anything, you understand? So that's why we are calling this one real. So that's a good way to remember. You get it. It's not something that is hard. You understand? In this case, we did not trace anything. So this guy's particular focus, it is real. This one is real. So let me clean that. Something. I'm just using that to explain. Please follow in class. You are meant to pay attention so that you don't miss any point and I say, where did that come from? No. But in this case, you know, we did tracing. So this guy is virtual. Are you getting me? Yes. So that's the idea. So this one is real because the converging rays are seen. Why the focus of a convex mirror is what? Virtual. Because the diverging rays are traced backwards. Do you see the idea? Yes. So generally in curved mirrors, generally in curved mirrors, the radius, we say R equal to 2F. Or you can say, or F equal to R over 2. And what is R? R is what? Radius of curvature. Are you with me? And F is focal length. So please get this formula. Let me put it in red, just like I normally do. Yeah, keep that in mind. Before we call it a day, we want to look at something very, very important. Something very, very important. We can't basically call it a day yet until we look at this. And this will take some time. So we want to look at the different images formed by both the concave mirror and the convex mirrors. So keep that in mind. So the idea here is see. Let's just give you images. Images. I'm going to start with the concave mirror formed by concave mirrors. I'm going to start with the first case. And that first case is, we say, when the object is at infinity. Images formed by concave mirror. When the object is at infinity, look at how I will construct. I'm going to give you what happens to the image. Number one, or we say the image is formed. The image is formed, or let's put it, instead of saying the image is formed, let's say the image is, when the object is at infinity, the image is, number one, is at F. Don't worry, we'll use diagrams to explain it. Number two, the image is real. Number three, the image is inverted. You see, this thing is what you will go and sit down with and read and study, memorize and understand with the diagram. So the idea is anyone you can do. If it's memorize, you can do memorize. If it's understand with the diagram, you can do understand. Because I'm going to draw the diagram straight ahead now. So when the object is at infinity, for concave mirrors, the object is at infinity. Let me show you how the diagram is formed. So you see that it is at F, it is real, it is inverted, it's smaller than the object. That smaller than object, sometimes they call it diminished. So that's the idea. So let me draw the diagram. This is our concave mirror. And I know that there is a principal axis always. Let me try to do that again. Let me just try to do it again. concave principal. So here we go. I know that this is the pole. I know that on this side, I have focus somewhere here. Now I have center of curvature, which is also 2F. You understand? So now I'm looking at. Let me extend this guy. Extend this guy. Oh, hold on. Oh no. Oh, good. Okay. So the object is at infinity. The meaning of that is that now I can't draw it on the principal focus or anywhere there. I'm just going to draw it somewhere outside here. Look at this. Let's say this is the object now at infinity. Let me come. Let me come here. Let me move the entire thing. Let me move the entire thing sideways. Oh, no. Yeah. So now I have this. Let's say this is the object standing up like this. That is the object is standing and facing up. Now I want to produce the image of this object. This is the object at infinity. What I will do is I'll trace it. Let me call it object AB. I'm going to trace it to hit the mirror. Trace it to hit the mirror. Then, of course, you know that when it hits the mirror like that, to bounce to this guy. And then this other part too, I trace it to hit the mirror. It will bounce to this guy as well. You see that? So when it bounces like that, if I keep it going, come in, give me a minute. Or better still, when I have, come on. Excuse me. Let me see. Yeah. So light bounce like that, and then the inverted, not up, not up there, not up there, it's down. I'm going to draw it here. This is where the image is formed. So this is object, this is image. So you see that the image is at F, CF right here. The image is, what we mean by real is that, definitely, it is in front. It's formed on the screen. It's not traced, it's not formed by traces. You get the idea? You get the idea? It's formed, it's real. Yeah, so then inverted, you discover that this guy that is up like this was the object. Meanwhile, the image is facing down now. So that's the idea of inverted. So like I used to say, whenever you cannot cram, you understand. See this, or you cannot memorize, you see this idea, it explains that real, inverted, and diminished or smaller than the object. You can see that in the original case, the object looked like as big as this. Let me not exaggerate it. It looked as big as this, but look at the image. It's almost half. So it has reduced in size. So that's just the point. So keep this diagram concept in mind. This one move like this, this one move like this, this one move like this, this one move like this. So this one move like this, yeah. So you get the idea. So that's just very straightforward something. So let's move to the other one. This is when the object, this is the case of when the object is at infinity. You have it real, it is formed at the focus, inverted, smaller than the. So let's go to the next one. And that is a case of when the object is beyond C. When the object is beyond C. So we'll repeat. And let's quickly say what happens. The image is number one. It's formed between, let me just write it, between C and F. Number two, it is real. Number three, it is inverted. Number four, it is smaller than object. And the idea is almost is similar because you have this curved stuff. I run my principal axis through, and then I have my F point. I have my C, which is also my 2F. And then when I say the object is beyond C, the meaning of that is this is C. It is somewhere in this side. So I can put it right here. You see when it's at infinity, yeah, at infinity, this was the principal axis here. Let me put a green line there. This was the principal axis. See, the object was beyond the principal axis. That's what it means by infinity. It didn't even touch the principal axis. See the object right here. It was beyond the principal axis. It didn't touch it. That's infinity. But now, since we are saying it is beyond C, the object is beyond C. Yes, it will be on the principal axis. To touch the principal axis somewhere. Let's put the object here. But that is somewhere beyond C, of course. That's obviously beyond C. This is C here. You understand? And this part is beyond C. So just get those points. I'm doing my very best to explain that concept to you. So this is where we place the object. So this is the object AB. Now, if I do the regular movement, the way I normally move, you get it? The way I normally move, that about 3 different movements I'm going to make now. And you will see it. Let's have it now. I'm going to move like this. You see that? And it will bounce. I'm coming. Hold on. Yeah, it will bounce this way. Yeah. But to pass through and keep going. Understand? Let's just keep that in mind. Now, the one down, you see this B part? Let me point at it with another color. This part here. I will also, let me point well. This part here, I'll also move there too. Just where I moved at the top here, I will move also at that part. So if I move at that part, I'm going like this. Let me use another color. Let me use red. I move on it and move this way and hit this place. And of course, I've said anytime they hit the mirror, they're always bouncing back to the focus. Just like this one when it moved. This one, when it moved like this, I'm using green on it now. When it moved like this, it bounced back to the focus. So this red one too now, move the way it moved and now bounce back. So it's moved like this first and now bounce back to the focus. And when it bounced back to the focus, it moved. Let's just extend it beyond. Yes, that's okay. Then the last movement we want to make is now the movement from the top here. Let me use which color? Let me create another color, blue. From the top here now, I will now move down diagonally. Move like this. through the center of curvature, I will move to C. So I'll move down, make sure I pass through the center of curvature. And then when I move down like that, I'm looking for how I will make sure that I strike. So let me extend my mirror. Well, hold on. Okay. So for my blue line, let me do it again. I'm moving through the center of curvature, that's C point, and I strike my mirror. And when I strike my mirror, I'm bouncing back. Because this time around, I'm not moving parallel. I'm moving diagonally. I'm not going to bounce back to the focus. I'm going to bounce back to the center of curvature. So whenever I move diagonally like that, and I pass through the center of curvature, I'm going to bounce back to that point. So this one is moving like this now, passing through the center of curvature, is hitting the mirror and bouncing back. So when it bounces back like that, we take note of where this black line, the one that I painted green and black that time, that bounced back to the focus here and goes beyond it. And you know, this other one, just for this red line, this red line, we don't really focus on it because it's the principal axis. It's not really doing any special thing. So that was why we even needed to create another one going through the center of curvature. So when we consider the center of curvature one and the black one, where they meet, this point here, let me give it green. This point where they meet, is where our image will now be formed. And this is the way it will be formed. Let me use black. This is where our image will be formed, and that's how it will be formed. If you look at the object looks like this. The image looks like this. So you can clearly see that if you observe the points we made, let me look for my red back again. Done. So observe the points we made. We said it is formed between C and F. Clearly, this is C and this is F, and the image is formed between them. That's correct. It is real. The meaning of that is like it is formed definitely on the screen. It's formed on the rear side. It's formed on the rear side of the mirror. So just keep that one as a point in mind. Then inverted, obviously, if the object is standing like this, the image is standing opposite, inverted. Then it is smaller than the object. Obviously, you can see that just by comparing these two. So let's go to the next point. That's C. You can see that this is how these things work. Object, when you place the object at C, now I'm going to give you the points and diagrams now, so you can go and study the diagrams to actually see what's happening there. The image is number one at C. So if you put the object at C, the image is at C. It is real. It is inverted. And it is same size as object. Same size as object. So keep that in mind. So at C, it is real, inverted, and same size as object. So keep that one in mind. Let me see. Let me give you the diagram for that. So right now, I'm going to draw the regular stuff. Mirror. By now, it should become a pattern to you. Principal axis. I know my focus is somewhere here. I know my C is somewhere here, which is also 2F. Are you following me? Yes. Now we are saying the object is at C. Let us see the object right here. We're now trying to form the image. So let's see. If I move it like this, I know it bounces back somewhere here. I'm going to move beyond that point and keep going. Then if I do the same thing for the top, since the bottom is lying on the principal axis. And so the bottom will not matter, because in the last time we saw that red line, this red line here, the red line at the principal axis did not have any effect. What we had to use was the one diagonal and the one top. So let's just do diagonal straight up. So I'm going to do the diagonal, which this time around, since the stuff is resting on C, I'm going to run the diagonal through F. So I'm running the diagonal through F. And running it through F this time, it's going to bounce sideways. It's going to bounce. I'm running it like this. So for me, it's going to bounce this way. It's going to reflect this way, not back. It's going to reflect this way. So, and if I did it properly, let me see. Let me go back and do it, because so let me see, run it through this. Okay, this is my focus, and then I bounce it to here. So I have a proper, if all my dimensions are correct, what I should have is that it is formed somewhere here. So this one is coming like this, this one is coming like this, this one is coming like this. So, and that point where it is formed is definitely going to be the center of curvature as well. So, but this is it. Yeah. So the idea is that this is the, let me put black now. This is the object, and this is the image. The idea is that they are formed at the same point, which is C. I mean, they exist at the same point, and that's the point we are making, that if the object is at C, the image will be at C. It will be real, but now you see that clearly it is inverted. This one is facing up. This one is facing down, inverted. It is the same size. You see that they look exactly the same size by the formation. So just please keep those points in mind. Keep those points in mind. So this is how you draw it. I have that. Now the next point, number 4. And that is when you have an object between F and C. Are you with me? What happens? The image is, listen attentively, is number 1, beyond C. Number 2, it is real. Number 3, it is inverted. Number 4, it is larger than the object. Are you seeing that? Very important. So let's now discuss the concept with diagram. You say if the object is at F, is between F and C. So let's draw our principal as this. Know that this is F. Know that this is C, which is 2F. The object is between F and C. That's somewhere here, right? Between F and C. Let's go to let's draw it well. Between F and C. That's the object. Take note of that. Let me not overdraw. I'm coming. Keep it at minimum height. So this is the object between F and C. I'm going to run it this way. This is how the diagram is produced. It goes through the focus, and I keep going, keep going, keep going. Then I don't run it down now. I run the diagonal from the top to the top. So this is how this one is produced. I run this here and run this one down. I'm now going to run one up, which will bounce back to return back. When it's coming back, it's going to come like this. So the idea is this one comes like this one comes like this, and then they meet somewhere here. If I extend my principal axis, I see something formed here. Oh, beautiful. It's not a perfect diagram, but I've painted the idea to you. I go again, this time around in red. This is where the object is, obviously between C and F. And I run one from here. See that? It bounces off through the focus and I extend it to keep going. Then I run one to the top, goes up, hits, goes up, hits that point, bounces back and starts coming, runs through. Let me extend in. Runs through, down, and they meet somewhere here. And I form my image right there. You see the idea? That's why we now say that the image is formed beyond C. You can see that beyond C is like this point. You know that that's always like back of C. So you can see that obviously the image is formed beyond C. We don't need to argue that one. You see it? It's formed what? Beyond C. Then it is real, of course. Then inverted. You see that the object, which is here, let me put green on it now, is right here. It's facing up. Meanwhile, the image is facing down. That's clearly inverted. It's larger than the object. The image is larger than the object. If you look at the image, let me put what color should I put on it again? Let me put blue. This time, done. See the object here. See how small it is. Like this. See the corresponding image. See it's big like this. So see that idea. Let me do that. That idea tells you that what? The image is what? Larger than the object. So we've made that point. Let's go to the next one, the fifth case. So this is meant for you to go and sit down and reproduce it. But most importantly, besides reproducing it and mastering it, also know the points, know what is happening, because they can be asked from you both in theory and OBJ. So this is where you know that you have work, you read. Don't just waste the time playing ball, doing very, very wonderful and serious things. Don't do that. You have work. And this is your work. You understand? You're not working you're not doing federal government. This is your work as a student. So number 5. Number 5. We're considering a case now. We've considered the number 4 case was when the object is between F and C. Now we are considering a case where the object is at F. Let's consider a case where it's at what? Is at F itself. So when is it that it is at F? Let's draw it again. Draw this guy. Draw the principal axis. Our focus right here. Center of curvature 2F. Keep things there. And then we put our object at F now. Object at F. Let me put it right here. See the object, F. And then let me start doing the usuals. I run it through here. And then bounces. Oh, I should have given you what happens to the image first. Let me give you what happens to the image. We say when the object has F, there's only one thing that happens to the image. The image is at infinity. It's at what? Infinity. That's the idea. So let's see how that happens in the diagram. At F, like I said, bounces through this one, bounces back through F. Then I keep it going. Oh, let me not bend by something. I keep it going. Yes. Now I want to do something, the same thing for that top. I run it up for this part. Oh no, don't run that. I run it up. See that? And I know that once it goes up like that, it bounces back and return. And so, let me come in. I run it up. Yeah. And then it goes up like that, bounce back and return such that return, yeah, passes through the center of curvature. I'm doubling my line, so I don't like that. So yeah, run it to the center of curvature. Yeah. So the idea is that when it's returning like that, the two of them return and they don't meet. So the idea of it being formed at infinity is that these returning lines don't meet. So this concept is now called at infinity. All the other lines have been meeting. So these ones, they return and don't meet. So let's go to the sixth idea so that we don't waste time. And that is the case where you have the object now between F and P and the pole. What happens to the image? The image is, number one, behind the mirror. It is not formed on screen now. It is virtual. It is erect. It is larger than the object. So let's paint that idea. We have our regular stuff of a mirror, a principal axis running through. Oh, form a line for me. So focus, C to F. See the idea? Now we are saying a case where the object now is between F and P. This is P. We know that this point here is P. So we are putting the object somewhere here, right? F and P. Let me zoom in there. So first idea is this time we're not just running stuff, we run up diagonally, up and down. So that's the idea. So I'm going to run one diagonal down like this. And so once it hits this point, it bounces like this. So let me create a line. Bounces like this. So that's the idea. Then when I run this other one up like this, it goes and now returns and bounces. Coming. Let me see. Let me draw this one. So this one has to be like parallel to that one. So this one is going like this. Yeah. And so this my center of curvature is too far safe. Let me put it there. See. Okay, so I give this up. What I know that is going to happen is that when this thing is returning, it's returning through this place. It's returning through this place. Yeah, so okay, that's how I have to give it. So that my line has to be drawn. Oh my God, I'm messing up the diagram, but notwithstanding, you get the point in the end. So yes, when this object hits this place, first it returns and returns through back to this, through the center of curvature. It returns through that point. So, but the idea here is that this other one, give me a minute. This other one that we drew first, that hit this place, it bounces more wider, more spread down. Like when it hit that place, it bounces. Why this top one, just bounces and passes through the center of curvature. Then we now use tracing. That's why in this case, in most of our other cases, we've been saying the image is real, but in this case, we say it's virtual. We now use tracing to trace where the image will appear. And so this is where the image will appear. It's not like tracing. So just get that idea. So that's why we say it's behind the mirror. Obviously, other ones have been on this side. Let me use a better description for on this side. Other ones have been on this side, but this time around, this one has itself on this side. So it's virtual. Clearly, we use tracing to form it. It is erect. The meaning of that is that the object is standing like this, and the image is standing like this. Both of them are facing up, so it's erect. Larger than the object, of course. You look at it, this is the object, this is the image. Which one is larger? The image is larger. So keep all these points in mind. And that's the interesting thing with the concave mirror. They have a lot of variation in forming their images. But a sweet thing about convex mirror, there is only one style of image. So we call it image formed by convex mirror. Convex or what? Convex or diverging mirror. In this case, the image formed by convex or diverging mirror is always, number one, let me just give you the features, always virtual, always erect, and always smaller than the object. So most of the time, this idea of smaller and larger, they call it diminished or enlarged. So when it's smaller, we call it what? Diminished. When it is larger, we call it what? Enlarged. Keep that in mind. When images are smaller, they are called diminished. Let me write it down. Note. When images are smaller, they are called diminished. And when they are larger, they are called enlarged. Are you getting me? Yes. So this idea of diminished and enlarged, you discover that the last point in this concave, this larger, you can say, okay, in brackets, enlarged. So another thing is that for the images formed by convex, you can easily abbreviate it to be VED. That's virtual, erect, and what? Diminished, VED, to always remember. So let's quickly go into mirror formula. Or let's talk about one thing before we go into mirror formula, magnification, and just one example before we call it a good day. It's been a long class. Maybe this class must have been broken into two, but no, we have a lot to cover, and so we can move it. So image, let's see, application. Let's talk about application of the reflection of light. Reflection of light. So we can say, number one, concave mirrors. Concave mirrors are used in torches. They are also used as concave mirrors let me not list it like that. I can say concave mirrors are used in torches. They're used in as shaving mirrors. They're used in car head lamps and in reflecting telescopes. Take note of that. So on the other hand, convex mirrors are used as driving mirrors. They're used as driving mirrors. And the reason is because they give erect image and have a wide field of view than a plain mirror. of same diameter. So just keep this point in mind. Let's now go straight into mirror formula. Mirror what? Formula. Very important. Very important. I'm going to write it straight up. 1 over F equal to 1 over V plus 1 over U, where F is the focal length. Oh, yeah. Or let me put it this way. Not focal length. Let's say F is. I'm coming. Hold on. Let me say. Okay. Let's say focal length. Let's say also call it final length. Just put it like that. Focal length or final length. Let's put it like that. V. Let's say V is image distance. U, object distance. Put it like that. Now, let's just talk about magnification. Might have mentioned this in previous class. So, but this is talking about how much bigger the image is than the object. So magnification is equal to image distance over object distance, or image size or height over object size or height. That is how it works. So just keep that in mind. Let's take one candid example before we call it a day. This is the example we used to call it a day. An object is placed 30 centimeters from a concave mirror, focal length 15 centimeters. Find the magnification of the image produced. Please listen attentively. Listen attentively. So whenever we are solving physics, we first identify what we are given. So solution to this problem, what are we given? We are given object placed 30 centimeters from a concave mirror. That they have given us object distance, 30 centimeters. They have given us focal length, 15 centimeters. They're asking us to find what? They're asking us to find the magnification. But in order to find magnification, we know that magnification is equal to V over U, but we don't know V yet. We are still looking for V. So let's find V by using mirror formula. 1 over F equal to 1 over V plus 1 over U. How do I do that? 1 over 15 equal to 1 over V plus 1 over 30. What happens? 1 over V, now I can leave it on that side and now say 1 over 15 minus 1 over 30. Very clear. Are you seeing that? So 1 over V will now be, do the LCM thing, 2 minus 1. And I get 1 over V to be 1 over 30. And what does that mean when I cross multiply? V equal to what? 30 centimeters. I've gotten V to be 30 centimeters. I can easily find my magnification to be what? V over U, which is 30 over U is 30. So my magnification is 1. And when you have your magnification is 1, it means they are same size. Assuming it was 2, it means that thing is twice as big. Assuming it was half, it means it was reduced by half. You understand? You understand what I'm saying? Assuming your magnification was 2, it means what? Twice as big, because it might be as big. You understand? Now that it is 1, is same size. Assuming it was half, it is what? Halved. The image is halved. So you get the idea. behind this thing. I will take one more example before we close. One more. We can do this. Let's take one more fresh example. So example 2. It says, find the expression for linear magnification produced by a concave mirror of radius of curvature R if U and V are the object and image distances, respectively. And so this one is just like a formula question. Respectively. Find the expression for linear magnification produced by concave mirror of radius R if U and V are the object. So the idea here is the solution is they did not give you, they're asking you to find an expression for linear magnification, and they did not give you this thing. They did not give you focal length, basically. Normally, we know that linear magnification is V over U, but they want you to at least create some other expression for it. So this particular question, let's not bother about this. Let's not bother about this because linear magnification is V over U, and assuming we wanted to even create, let me just make an interpretation from this question. If you are looking for focal length from radius of curvature, we know that F equal to R over 2. I think up above, let me go straight to that place. Up above, somewhere up right here, we wrote that expression where we said F equal to R over 2. Yeah, see there. So keep that in mind. Assuming we are looking for F from, so just keep these two in mind. That's what I would just say. So, but magnification is always V over U. So this question is not, sorry about the structure of the question, but these are the, at least I was able to remind you of this one. F is equal to R over 2. So just keep that in mind. And yeah, let's wrap it up for today. And please make sure you study more. For my very particular audience, I sent you an assignment. Assignment 1, make sure you do it. So then let's talk about the uses. Oh, we've talked about the uses of curve mirror already, where we talked about, where we talked about convex use for touches and all of that. So we'll call it a day at this junction. I will see you in the next class, and goodbye.